On a standard military radar screen, a surface vessel of typical dimensions announces its presence with an unmistakable, glowing footprint. It is an unavoidable consequence of traditional naval architecture. Massive walls of gray steel, flared hulls designed to deflect the punishing geometry of the open ocean, and sprawling superstructures bristling with exposed antennas, radar dishes, satellite domes, and weapon mounts. Every single one of these metallic surfaces acts as a perfect geometric reflector, bouncing electromagnetic energy straight back to an enemy's receiver. To an opponent equipped with modern over-the-horizon radar, a traditional surface combatant does not merely show up. It screams its presence across hundreds of miles of open water. But out in the volatile, windswept expanses of the deep blue sea, there exists a massive anomaly that completely defies the established laws of naval detection. It is a 16,000-ton mountain of specialized steel, complex carbon fiber composite armor, and cutting-edge military engineering. By every historical metric of maritime warfare, a vessel of this staggering displacement should possess a radar cross-section roughly equivalent to a floating skyscraper. Yet, when an enemy operator sweeps the horizon with standard marine tracking equipment, this multi-billion-dollar Titan registers as nothing more than a small, insignificant commercial fishing boat, or perhaps a displaced wave crest shifting casually across the water. This is the USS Zumwalt, designated DDG-1000. It is simultaneously the most financially staggering, intensely controversial, and technologically sophisticated destroyer ever conceived, designed, and constructed by human hands. It represents a radical, multi-billion-dollar departure from over a century of traditional naval philosophy. This machine was not built merely to iterate on the successes of the past. It was engineered to completely rewrite the rules of global maritime engagement. It is a vessel designed from the keel up to operate entirely within the tactical shadows of the modern battle space, to generate an unprecedented amount of raw electrical power capable of illuminating a medium-sized metropolitan city, and to project devastating kinetic force against land-based targets located thousands of miles away, all before an adversary even registers that a hostile entity has breached their territorial waters. The existence of the Zumwalt class is the result of a profound institutional realization within the halls of the Pentagon. As anti-ship cruise missile technology advanced and became widely proliferated among near-peer adversaries, the traditional methods of defending a surface fleet began to face a crisis of economic and physical sustainability. For decades, the primary defense of a naval strike group relied on layering interceptors, firing incredibly expensive surface-to-air missiles to destroy incoming threats. But what happens when an adversary can deploy waves of low-cost, sea-skimming missiles or asymmetric swarms of explosive drones that outnumber your available interceptors? The ultimate solution was not just to build a better shield, but to construct a ship that could avoid being targeted in the first place. The most effective defense against an incoming missile is ensuring the enemy cannot find an asset to lock onto. Thus, the concept of the low-observable surface combatant was born. The United States Navy did not just want an evolutionary update to its existing fleet. It demanded a revolutionary leap forward. They envisioned a capital ship that could approach an enemy's coastline with total impunity, mapping out defenses, jamming communication arrays, and striking critical command and control infrastructure with pinpoint accuracy. This ambition gave rise to a design program that would push the absolute limits of material science, hydrodynamic engineering, and software automation. It resulted in a ship that looks less like a traditional vessel of war and more like a sinister, angular stealth bomber engineered to glide effortlessly across the surface of the ocean. However, the path to innovation is rarely smooth, and the story of the USS Zumwalt is as much a cautionary tale of strategic overreach as it is a triumph of engineering. Right now, hidden beneath the carefully managed public image of the United States Navy's active surface fleet. An intense, quiet internal doctrinal war is being waged. It is a conceptual battle between this radical, $9 billion ghost ship and the brand new Arleigh Burke Flight III destroyer, a hyper-modernized, heavily armored variant of a classic hull design that some of the world's leading naval strategy experts claim is actually the true, undisputed king of the ocean. While the Zumwalt represents the ultimate expression of specialized, high-tech stealth, the Arleigh Burke Flight III represents the pinnacle of versatile, survivable, and mass-producible combat power. To truly understand the balance of naval power in the modern era, one must look past the sleek lines and the public relations briefings. We must conduct an exhaustive, system-by-system investigation into the absolute belly of these metal beasts. We must journey from the highly classified, softly lit command spaces, where a handful of operators control the destiny of the ship, down to the cavernous, automated weapon bays that hold the world's most terrifying arsenals, and finally into the roaring, high-voltage engine rooms where revolutionary power plants provide the lifeblood for future weaponry. In doing so, we will uncover not only the immense capabilities of these ships, but also the complex geopolitical and economic shifts that forced the United States military to build the ultimate futuristic warship, only to completely alter its operational purpose in the face of a changing world. To fully comprehend the sheer scale of the engineering achievements integrated into the Zumwalt class, one must examine its foundational structure, the hull itself. For more than a century, the evolution of modern warship design has favored a distinctly outward-sloping hull architecture. Look closely at any standard cruiser, destroyer, or frigate slicing through the ocean, and you will notice that the sides of the ship flare dramatically outward as they rise from the waterline toward the main deck. This structural choice is rooted in deeply established principles of naval architecture and hydrodynamics. An outward-flaring hull provides a vessel with excellent reserve buoyancy. As the ship rolls heavily into a wave, the widening hull displaces an increasing volume of water, generating a powerful natural righting arm that forces the ship back toward an upright position. Additionally, this classic design naturally pushes aggressive waves away from the superstructure, keeping the deck relatively dry and protecting exposed crew members and sensitive equipment from the brutal impact of sea spray and salt corrosion. The designers of the USS Zumwalt, however, deliberately chose to abandon this century of maritime wisdom in pursuit of an entirely different priority: absolute radar cross-section minimization. In place of the traditional outward flare, they resurrected and completely revolutionized a historical architectural concept known as the Tumblehome hull. Instead of widening as it rises from the sea, the hull of the Zumwalt narrows significantly as it moves upward toward the main deck. The sides of the ship slope inward at a sharp, calculated angle, creating a clean, geometric silhouette that looks completely alien to traditional mariners. This inward-sloping geometry is a fundamental requirement for advanced radar stealth. When an enemy radar installation, whether situated on a distant coastline, an airborne early warning aircraft, or an opposing surface vessel, transmits an electromagnetic scanning pulse across the ocean, those radio waves travel horizontally through space until they strike an object. If those waves impact the outward-sloping side of a standard warship, the perpendicular angle of the steel acts like a mirror, reflecting a clean, high-intensity signal directly back along the path it came, instantly revealing the ship's precise position, heading, and approximate size. But when those same radar waves encounter the sharply angled, inward-sloping walls of the Zumwalt's Tumblehome hull, the laws of physics work against the tracker. Instead of bouncing back to the source, the electromagnetic energy is scattered harmlessly upward into the atmosphere or down into the absorbing surface of the water. Every single exterior surface of the ship is subject to this rigid geometric discipline. There are no vertical walls, no right-angle corners, and no exposed structural beams to create a corner reflector effect, which is the primary cause of large radar returns on conventional vessels. Achieving this level of low observability required an unprecedented partnership between hydrodynamicists and radar signature specialists, two groups whose design goals are historically in direct opposition to one another. To make the Tumblehome design viable in heavy seas, the bow of the ship had to be completely reimagined. Rather than riding over the tops of incoming waves like a standard flared bow, the Zumwalt features a wave-piercing bow that slices cleanly directly through the heart of swells. This knife-like entry minimizes pitch variations, providing an incredibly stable platform for weapons and sensors, and reducing the massive hydrodynamic wake that can be easily spotted by overhead satellite reconnaissance. However, the implementation of a Tumblehome hull brings severe engineering challenges that kept naval architects awake at night during the ship's development phase. The primary concern is stability under extreme conditions. Because the hull narrows at the top, a Tumblehome ship loses reserve buoyancy as it rolls into a wave, a characteristic that is the exact inverse of a traditional ship. If a Tumblehome vessel rolls past a certain critical angle of heel, the natural righting forces can degrade rapidly, creating a risk of capsizing in severe, following seas where massive waves approach the ship from behind. To mitigate this inherent vulnerability, the engineers integrated advanced, highly sophisticated computerized ballast management systems. This system constantly monitors the ship's center of gravity and fluid dynamics in real time, rapidly shifting thousands of gallons of fuel and seawater between internal tanks to dynamically stabilize the vessel against the erratic forces of the ocean. The geometric shaping of the hull, while critical, represents only the first layer of the Zumwalt's multi-layered stealth architecture. To achieve a radar cross-section 50 times smaller than a standard guided missile destroyer despite its massive physical dimensions, the ship's exterior skin had to be treated with advanced material sciences derived from classified aerospace programs. Every square inch of the vessel's exterior is an intentional combination of structural strength and electromagnetic energy management. A significant portion of the Zumwalt's massive deckhouse, the central superstructure that rises above the hull, is constructed not from traditional naval steel, but from incredibly advanced, lightweight carbon fiber composite materials. This composite superstructure offers dual advantages. First, it significantly reduces the top weight of the vessel, lowering its center of gravity and directly offsetting the inherent stability liabilities introduced by the Tumblehome hull design. Second, carbon fiber composites possess entirely different electromagnetic properties than raw steel, allowing engineers to integrate specialized radar-absorbent materials directly into the structural matrix of the ship. These radar-absorbent applications consist of highly classified tiles and coatings formulated from iron ferrite compounds embedded within a durable, carbon matrix polymer. When an incident radar wave strikes these specialized materials, it does not simply reflect off a hard surface. Instead, the alternating magnetic fields of the radar pulse interact with the microscopic iron particles within the tiles. This interaction induces rapid magnetic molecular friction inside the material, effectively converting the high-frequency electromagnetic energy of the enemy's radar wave into low-grade, harmless thermal energy that is quickly dissipated across the ship's skin. Through this process, up to 98% of the incoming radar energy is completely absorbed, leaving almost nothing to return to the enemy's receiver. Furthermore, the integration of sensors into the superstructure represents a masterpiece of low-observable engineering. On a standard Arleigh Burke-class destroyer, the upper decks are a chaotic forest of rotating radar dishes, whip antennas, satellite transceivers, and electronic warfare enclosures. Each of these structures features distinct vertical lines and complex shapes that illuminate an enemy radar screen like a Christmas tree. On the Zumwalt, this clutter is completely eliminated. Every single antenna, communication array, and sensor system, is entirely enclosed within flat, passive, multifunction aperture panels that are flush-mounted directly into the angled faces of the composite deckhouse. These panels are covered by specialized frequency-selective radomes, materials that allow the ship's own radar and radio frequencies to pass through cleanly while presenting a perfectly flat, radar-reflective shield to any external scanning frequencies. Even the ship's physical weapons are subject to this intense material discipline. The massive dual 155mm advanced gun system turrets situated on the forward deck do not feature exposed, cylindrical barrels that would compromise the ship's clean geometry when the guns are not actively engaged in firing operations. The massive barrels are automatically retracted and completely enclosed within heavily faceted, stealth-shaped housings. The entire forward deck remains a seamless, unbroken sheet of angled steel and composite paneling, offering no distinct edges or anomalies for an opponent's tracking algorithms to identify. Moving from the exterior stealth skin into the interior structural architecture of the USS Zumwalt reveals a total rethinking of naval survivability and weapon storage. For the past 4 decades, the standard configuration for vertical launch systems across nearly all global navies has relied on a centralized block layout. On a typical modern warship, such as the standard variants of the Arleigh Burke class, the missile cells are grouped tightly together in massive, multi-cell blocks located deep within the center line of the forward and aft decks. This configuration is highly efficient from a space utilization standpoint, allowing a massive concentration of firepower to share centralized power distribution, cooling lines, and digital data networks. However, this centralized configuration introduces a catastrophic vulnerability in high-intensity combat. If an enemy anti-ship cruise missile, torpedo, or asymmetric suicide drone manages to penetrate the ship's primary defenses and strike that central missile magazine, the resulting sympathetic detonation of dozens of closely packed rocket motors and high-explosive warheads will instantly tear the ship apart. A single successful strike to a centralized vertical launch block frequently results in the complete, catastrophic loss of both the vessel and its entire crew, as seen in numerous historical naval engagements. To eliminate this single point of failure, the engineers of the Zumwalt class developed a radical, distributed ordnance architecture known as the Peripheral Vertical Launch System, or MK-57. Instead of clustering all the missile cells into a single vulnerable vault in the center of the vessel, the Zumwalt's 80 advanced launch cells are split into separate 4-cell modules that are distributed along the outer edges, or periphery, of the entire hull. This layout transforms the entire internal volume of the ship, utilizing spaces that were previously considered dead space or simple fuel tankage to create an innovative defensive barrier. The design of each module is a marvel of armored containment and pressure redirection. Each cell is encased within an immensely strong, heavily reinforced structural vault built from high-tensile, shock-hardened steel and blast-absorbent composite liners. The critical innovation lies in the specific path of least resistance engineered into the vault's geometry. The inner wall of the missile cell, which faces the interior living spaces, engine rooms, and command centers of the ship, is heavily armored and structurally reinforced to withstand immense overpressures. Conversely, the outer wall of the cell, which forms a portion of the ship's exterior hull skin, is engineered with precise structural scores and blowout panels. If a catastrophic event occurs, whether an enemy missile strike punctures a missile bay, or a technical malfunction causes a solid-fueled Tomahawk or evolved Sea Sparrow missile to ignite inside its sealed canister without launching, the system's passive safety engineering takes over instantly. The immense heat, expanding gases, and explosive overpressures generated by the burning rocket propellant are physically prevented from breaching the heavy internal armor wall. Instead, the force easily shears through the external blowout panels, directing the entire catastrophic explosion outward away from the ship and directly into the open ocean. Through this design, even a direct hit that detonates multiple internal missiles will only destroy that local four-cell module, leaving the core structure of the ship, its propulsion systems, and the vast majority of its crew completely unharmed and capable of continuing the fight. Despite the brilliance of its safety